This is what 3,600 horsepower looks like when it grenades inside its own crankcase. In 1985, the most powerful locomotive manufacturer on Earth quietly killed its newest locomotive program after just 18 months of production, and the internal reports from the LaGrange test floor have never been published. What did EMD see inside those engines that scared them badly enough to surrender the #1 spot they had held since 1939 and never reclaim? Shredded metal sprawls across the test bay floor, each jagged edge a frozen moment of violence. The block is split wide, crankcase walls peeled open like the aftermath of a shell burst. Cast into the iron, a serial stamp, U645, FA8404R137, anchors the wreckage to a single winter on the LaGrange assembly line. This is not rumor or legend. This is the artifact itself, the 16-cylinder heart of Union Pacific 3806, one of the infamous heavy block test units that ran hotter, harder, and faster than any EMD engine before it. A deep punch through scars the lower web, connecting rod fragments fused to scorched alloy, oil channels blackened by fire. The block's surface still bears the faint grid of foundry marks, the date code matching the fourth quarter of 1984, when EMD rolled the dice on 3,600 horsepower and locked their future to a single, uprated design. No paperwork softens this reality. No service bulletin can erase the gouges left by catastrophic main bearing failure. The physical evidence sits in silence, daring anyone to question the official story that this was just another locomotive, just another engine, not the centerpiece of a corporate gamble that detonated in plain sight. Every fracture, every scorched edge, is a ledger entry written in steel. The only question that remains is how many others were quietly buried, their records sanitized, their defects reclassified, as the company shifted the narrative from disaster to upgrade. The block is the witness. The story it tells is not just about horsepower, it is about everything that was lost the moment the crankshaft let go. The ledger tells a story the marketing brochures never dared. Bound in worn covers, the original defect logs from LaGrange catalog, an average of 26 to 28 faults for every SD50 that left the test floor between 1983 and 1985. These are not rumors or anecdote. Each entry is signed by the test engineer, the foreman, and the quality assurance officer, every signature a silent admission that something fundamental had gone wrong. Defects are coded by severity, A for immediate safety failures, B for performance issues, C for cosmetic flaws. The A column fills with crankcase cracks and bearing pitting. The B column lists turbo lag and oil leaks. Even the C column, meant for minor errors, stretches on with misrouted harnesses and mislabeled panels. The numbers strip away any illusion of an isolated event. 523 SD50 locomotives were built worldwide, 431 for US railroads alone. Each one was tracked by serial, defect count, and corrective action, the data preserved on microfilm and in digital scans at the University of Texas Railroad History Archive. Shelf code Box 3, Folder 12, digital checksum stamped for provenance. Every ledger page is a brick in the wall of evidence, each defect entry a nail in the coffin of the 645F's reputation. The phrase 25 plus defects per unit is not a myth, it is a statistical reality, confirmed by the ledgers and echoed in shop repair orders and field warranty claims. These ledgers are the silent guardians of the truth, holding the company to account long after the production lines fell silent. Before the first boardroom memo called for damage control, the numbers had already written the verdict. This was not a single failure, but a systemic unraveling, measured in hundreds of engines and thousands of unresolved faults. In the early 1980s, EMD's grip on North American railroads was absolute. The SD40-2, their 6-axle workhorse, hauled everything from coal drags to intermodal stacks, its 3,000 horsepower engine the industry's gold standard. But in boardrooms from LaGrange to Detroit, a new threat was circulating, printed in glossy color on General Electric's latest C36-7 spec sheet. General Electric, once an afterthought, now promised 3,600 horsepower, 6 axles, and a reliability record that crept ever closer to EMD's own. The numbers were impossible to ignore. 4,400 gallons of fuel capacity, 16 cylinders, and a continuous tractive effort that matched or beat anything EMD had on the rails. Inside EMD's headquarters, the sales brochures grew defensive. Phrases like proven reliability and unmatched service life were stacked against General Electric's bold claims of higher horsepower and lower maintenance. The board minutes from October 1979 record a single line that read, "Review of 645F development schedule and competitive positioning against General Electric's 3,600 horsepower offerings." The handwriting is tense, the stakes clear. If EMD failed to answer General Electric's challenge, the market would shift, first by inches, then by miles. Pressure mounted as railroad procurement teams demanded more. Union Pacific and Missouri Pacific both requested horsepower guarantees in their next orders. General Electric's C36-7 spec sheet circulated in the boardroom, highlighting its 3,600 horsepower output and its ability to run harder, longer, and cooler than anything EMD had fielded. The old playbook, incremental upgrades and steady improvement, no longer satisfied the men with the checkbooks. EMD's leadership issued a directive: match General Electric at 3,600 horsepower, no matter the engineering risk. The legacy of dominance was now shadowed by urgency. The horsepower race was no longer a matter of pride, it was corporate survival. And in that moment, the SD50's fate was sealed, not by a single design flaw, but by the relentless pressure to outgun the competition at any cost. Contracts inked in November 1984 forced EMD's hand. The ink was barely dry on Missouri Pacific's order for 60 SD50s, each one promised at the full 3,600 horsepower, each one a bet placed at the edge of the design envelope. The LaGrange production floor was already running at capacity, but the boardroom commitment meant there could be no retreat. The Missouri Pacific order, signed November 23, 1984, called for heavy block 645F engines, locking the uprated design into mass production before the first field test had cooled. Unit numbers SD50 to 2001 through SD40 to 2060 lined the build ledger, with the first completed in March 1985, and the last rolling out just before Christmas that year. 2 units never left the line, scrapped after dynamometer testing revealed early crankshaft failures. The rest shipped into a waiting market, their fate sealed by the same signatures that had demanded more power, faster. The corporate merger that folded Missouri Pacific into Union Pacific at the start of 1986 only deepened the commitment. On January 15, 1986, Union Pacific's capital program absorbed all 60 units, rebranding them as Union Pacific SD50-2. The order represented $120 million in 1985 dollars, a figure that covered nearly 7% of EMD's planned 645F output for the year. Tooling for the heavy block crankcase, costing over $9 million, was amortized across this run, making a design rollback financially impossible. Trade press announcements fanned the flames. Railway Age called it the largest single order for a 3,600 horsepower locomotive in North America. Every press release, every public statement ratcheted up the pressure to deliver on the promise, even as defect logs piled up in the shadows. The dice were cast. There was no pause, no contingency, only the relentless forward motion of production lines and corporate ambition. The SD50 fleet was now a matter of public record, and the only way out was through. Union Pacific's heavy block SD50s were meant to be the ironclad proof of EMD's horsepower gamble. Instead, they became the first casualties. The test logs for Union Pacific 3805 through 3808 read like a disaster checklist: main bearing cracks, connecting rod bolts sheared, turbochargers surging off design limits. Cylinder head temperatures climbed 35 degrees above the engineering ceiling, redlining the cooling system and warping the block's geometry. Within weeks, the defect columns swelled: A codes for catastrophic failures, B codes for crippling performance losses, and C codes for the cosmetic errors that trailed every rushed build. The numbers told a story no press release could spin. In the first quarter of 1985 alone, defect tallies for the heavy block fleet surpassed 120 entries, with over half flagged as safety critical. Crankcase fractures appeared not as outliers, but as a pattern, each one traced to the same elliptical web and overstressed fillet. Internal memos from Union Pacific's Omaha office warned of a systemic fatigue issue, language that would never reach the public. Warranty claims spiked. Field crews reported metallic debris in the oil, engines seizing in the middle of a consist, and blocks splitting open under load. Every failed test, every shredded crankcase forced another engineering workaround. Governor speeds were dialed back, injector timing was retarded, and coolant pressure limits were raised. Yet the failures kept coming, relentless and uncontained. The defect logs became a grim roll call, bearing spalling, rod punch through, turbo surge, electronic control faults. The heavy block units, intended as proof of concept, became canaries, sacrificed in the name of a power rating that the engine could not survive. As the bodies piled up, the urgency shifted from innovation to damage control, with every new failure erasing another layer of corporate denial. Mechanical departments across North America became triage wards, working to contain a crisis that refused to be named. The first wave of countermeasures swept through shop floors and division offices as service advisories multiplied. Locomotive power assemblies, LC-114 modules, were pulled and replaced with the reinforced LC-118 units wherever possible, each swap a silent attempt to buy time against the rising tide of failures. Governors were recalibrated in the field, dropping maximum engine speed from the original 954 revolutions per minute to 926, then again to 904, each reduction quietly erasing a slice of the promised horsepower. Injector timing was retarded by 3 to 4 degrees before top dead center, a move intended to blunt peak cylinder pressures and stave off the next catastrophic rod punch-through. Every bulletin read like a confession. EMD's service instructions, issued in rapid succession from late 1985 through 1986, charted a retreat from the original design. LC-114 to LC-118, RPM cuts, timing shifts, and cooling system tweaks. On some lines, entire fleets were derated on paper. Canadian National's SD50Fs were officially listed at 3,300 horsepower. CSX's units were capped at 3,000 by a 2006 service order, and Norfolk Southern's SD40E rebuilds stripped the 645F of its identity altogether. Each reclassification, each module swap, each firmware patch became a line item in a growing ledger of containment, not cure. The cost was measured not just in parts and labor, but in the quiet rewriting of the engine's history. What began as a campaign to outpace General Electric's -7 became an endless cycle of symptom management. As failures mounted and the original engineering promises faded, the drive for root cause gave way to a culture of workaround and redefinition. The official record, softened by technical bulletins and derating memos, buried the scale of the disaster beneath layers of authorized language, leaving the true autopsy for another day. The decision to chase 3,600 horsepower set off a chain reaction inside the 645 that no engineer could unwind. The uprate was not just a number on a brochure, it was an 11% surge in inertial load forced through every bearing, web, and journal by a single change. The governor set point. From the original 900 revolutions per minute baseline, the heavy block engines were pushed to 950, then fine-tuned to 954 revolutions per minute, each increment compounding stress across the crankshaft. On paper, the math was simple. In practice, it was catastrophic. Rotational forces scale with the square of speed. At 950 revolutions per minute, every revolution hammered the elliptical crankwebs with forces the old circular design had never seen. The finite element models run late at night in LaGrange's engineering office mapped out the hotspots, main bearing fillers glowing with simulated stress, web roots showing spikes where the geometry narrowed. The elliptical web, meant to save weight and accommodate the interlocking jigsaw crankcase, instead became a stress concentrator. Where the old 645E's round web diffused load, The 645F's new profile focused it like a lens burning a hole in paper. Test logs from the Union Pacific 3805 to 3808 prototypes recorded the numbers without sentiment. At full load, with the governor locked at 954 revolutions per minute, bending stress at the main journal fillet reached 210 megapascals, a 15% jump over the previous generation. The finite element models predicted fatigue life dropping from 1.2 million cycles to just under 900,000. Metallurgical analysis of failed shafts confirmed the model: cracks radiating from the inner radius of the elliptical web, subsurface inclusions acting as nucleation sites, beach marks tracking the relentless march of high cycle fatigue. The jigsaw crankcase, designed to stiffen the block and reduce casting flaws, did its job, but at a cost. By rerouting bearing reaction forces directly into the crank web, it amplified bending moments where the geometry was already weakest. Stress rises at the web fillet transition became fracture origins, invisible until the first ping echoed through the block and oil pressure dropped to zero. Engineers traced the failure path in cold detail: initiation at the web root, propagation through the fillet, catastrophic separation as the crankshaft let go. Each event left behind a forensic signature: striation spacing at 30 microns, matching the predicted crack growth rate for 954 revolutions per minute operations. The numbers were inescapable: an 11% increase in inertial load, a 15% rise in peak stress, and a fatigue life cut by a third. The elliptical web, the jigsaw crankcase, the uprated revolutions per minute, each change justified in isolation, each one a step toward the breaking point. The design team's calculations lay bare on the page. The SD50's power came at the price of structural integrity, and every block that left LaGrange carried the same mathematical flaw. The machine was now a loaded gun, cocked by corporate mandate, waiting for the next high-speed run to pull the trigger. Under the lens of a scanning electron microscope, the fracture face of a failed 6445F crankshaft tells its own story. Striations ripple across the steel, each one a record of fatigue cycles endured and lost. At the journal fillet, the microstructure is torn and pitted, evidence of high cycle fatigue that no service bulletin could disguise. Metallurgists from the Electromotive Division lab logged the findings in quiet, technical language: transgranular cracks, initiation at the web root, beach marks tracing the relentless pulse of 954 revolutions per minute. The scanning electron microscope imagery, archived in the LaGrange materials vault, shows the same pattern across every examined shaft, a forensic signature that links field failures to the design geometry itself. The elliptical web and jigsaw crankcase, meant to save weight and stiffen the block, instead focused stress at a single, fatal point. Inside the boardroom, the verdict arrived not as a dramatic announcement, but as a typed memo. Dated January 1986, stamped "Confidential," the so-called kill order ended 645F production with a single line: cease all further SD50 assembly, effective immediately. The minutes from that meeting, later unearthed in the Progress Rail archives, reveal the calculus behind the decision. Warranty reserves were exhausted. Field failures outpaced corrective actions. The cost of retooling for a new engine was less than the cost of another year of defect claims. The 645F program was terminated, not with public explanation, but with a quiet shift in corporate strategy. The consequences rippled outward. By 1995, General Electric controlled 55% of the North American high-horsepower locomotive market, a lead built on the reliability vacuum left by Electromotive Division's collapse. The market share that Electromotive Division had owned for nearly half a century was now gone, surrendered in the span of a single product cycle. The SD50's mechanical autopsy became a cautionary tale in boardrooms and engineering schools alike, a reminder that the true cost of failure is measured not just in broken engines, but in lost decades. On a timeline stretching from the 1984 uprate to Electromotive Division's final North American production in 2014, the ARC is unmistakable. Each tick marks another retreat: the 645F's quiet discontinuation, the rise of the 710G, the slow bleed of market confidence, and finally, the end of domestic manufacturing. The forensic trail, scanning electron microscope micrographs, board minutes, kill memos, forms a chain of evidence that no amount of marketing language could erase. The fracture was not just in steel, but in the corporate identity of a company that once defined American railroading. What remains is a record written in metallography and market share, a story of how one engine's failure became the dividing line between dominance and decline. Steel fractures. Records vanish. In the void left by EMD's silence, GE's flag still flies over American railroads, 4 decades and counting. The SD50's downfall rewrote the rules. Transparency is not just good engineering, it's survival. When the truth about failure is redacted, the market never forgets who paid the price. Some wreckage, even buried, casts a shadow that never lifts. Let us know your take in the comments.